Hey everyone, Krishna this side, and I welcome you all to this channel. So let's solve this LeetCode question 421 maximum sort of two numbers in an array. Today's lead question is quite easy. So yes, decided to cover this one. Let me read the problem statement. Given an integer array nums, we have to return maximum result of nums of i's or nums of j, where 0 less than equals to I less than equals to j less than n. So basically, we have given an array. In this array, we have to pick any two numbers and we have to perform XOR operation between them. Whatever the result that we are getting it should be maximum, correct? So we can pick either 310, 35, 325 or 525, 52 like that, and we have to perform XOR operation. So the best result we can get is between this 5 or 25, which is 28, and that is something what we have to print into the output. Okay, I guess this question is pretty much clear. And if we look into the constraint, this nums dot length, that is the array's length, is basically 10 to the power of 5. That means if we try to write this code in brute force way, like we will start first for loop from 0th index, second for loop from let us suppose first for loop is basically pointing I, which is basically pointing to 0th index. Then second for loop start from next index onwards, so it will be j. Okay, j basically I plus 1, from there it should start. And this way we will keep on checking two numbers, like for first 3 with 10, 3 with 5, 3 with 25, 3 with 2, 3 with 8. And we get the results. So at any point in time, XOR operation between any two numbers, if it is maximum, we will keep on updating it into a variable, and that is something what we can return. Okay, that is brute force way. And if we see that, it is basically n square time complexity, and with these constraints, definitely will hit with TLE. So we have to make sure that whatever the answer that we are writing it should be either n log n or less than that. Correct. So that is something what I'll discuss with you, and once I explain you this approach, whatever that I am having, I'll write down the code as well. Okay, let me connect the screen first. Okay, let us suppose this is the array that is being given to us, and we have to perform XOR operation. That could be any two numbers, and whatever the XOR operation between them, answer that we are getting, we have to get the maximum result from there. Correct. So see, the first thing is like whenever any particular decimal number that is given, if we want to convert it into the binary number, how we basically represent it? So it is like for this 4, it is going to be 1 0 0, right? So here to the power of 0 1 2, and this goes all the way. If it is an integer, it will be to the power of 31. So all these rest bits are 0 0 0. Correct. So now same goes with 5, like it is going to be 1 0 1. So it is like to the power of 2 into 1 plus to the power of 1 into 0 plus to the power of 0 into 0. So when we sum them up, the answer is going to be 4. Here it is going to be 2 plus 0 plus 1, it is going to be 5. Okay, this way we normally represent any decimal number into binary formation. Correct. So whenever we are performing XOR operation between any two numbers, so these bits that we are getting, like for 4 it is like this, for 5 it is like this. When we are performing XOR operation between any two numbers, ideally the XOR between 1 1 is going to be 0, 0 1 is going to be 1, 1 0 is going to be 1, 0 0 it is going to be 0. How this happens is like whenever we have odd number of ones, and when we are trying to perform XOR operation, the answer is going to be 1. At any point in time, if we have even number of ones at that time, okay, 1 means like this set bits that we have, that is something what I'm counting. So if we have even number of ones, here it is going to be 0. So that's how this operation basically looks like. So whenever we are performing XOR operation between any two numbers, if we want to get the maximum answer, okay, obviously both the bits that we have at each level, here here here, so these bits should be different. Okay, opposite bits should be there. So here if we have 0, it should be 1, then only this answer is going to be 1. And at any point in time, if these results are basically 1 1 1 like this way, obviously this answer is going to be uh, big. Correct. So we have to make sure that whatever numbers we are picking, right, at each level, these bits should be different, then only we can get the best answer, right? So here only these two pairs have different values, so it is going to be 1. All these values are going to be 0 0. So whenever we are performing XOR operation between 4 and 5, the answer is going to be 1, because this decimal representation of this particular binary number is going to be 1. Correct. So I guess this particular thing should be known to all of us before writing this one. Now we are clear that at any point in time, whenever we are trying to perform XOR operation between any two numbers, the bits should be different. Okay, at any point in time. So if we have 4, Okay, so at any time point in time, this 4 is actually integer. So in an integer we can have 32 bits. In Java typically I'm saying, so 32 bits we have. The first bit is going to be signed and rest all the bits basically represent that particular number. Okay, that is for representing that number we basically use all the rest 31 bits. So these 31 bits in these 4s are basically 0 0 0 0 all the way 1 0. Okay, this is how these bits basically represents, right? So it goes all the way to the power of 31, right? So obviously if in this particular array we have maximum value integer dot max, okay, if that is also available with us, this integer dot max is going to be like one kind of like this at the end, like it will start 31 bit going to be 1 31st bit. So whenever we are trying to perform XOR operation between this integer dot max and 4, obviously here it could be 1 1 like this. It goes all the way to like 1 1 1. At this point in time, the answer is going to be typically maximum. That is something what we can notice. So yes, the idea is clear now. So what we can do is with the help of these numbers that we have, we can actually try to generate a trie. Okay, and in that try what we can do is we can, because see at any point in time these numbers bits that are available at each level, they can be repetitive, and I don't want to store them at each level. I don't want to store them separately, because 4 is basically represented as like 0 0 0 0 all the way to 1 0 0, and 5 is basically represented as 0 0 0 0 all the way to 1 0 1. So obviously all these bits are same, even these bits are same, only a extra bit that is there are like these bits. So obviously for them, like I don't want to keep on storing these bits in different areas. I don't want to create separate nodes for them. So best is like we can use try. In the try, if the bits are same, we can follow that particular path and we can build that particular one. So the first thing that we can do is we can create a try. And why we are creating try, the idea is pretty much clear. So at any point in time, if I have bit that is available here, 0 bit is available in the try, we will be having two children. Okay, at each level we will be having two children. So from root level, so this is our root. For this one we will be having two children. The first is going to be set 1 bit, second children is going to set 0 bit. So at any point in time we encounter 0. Okay, for this 4, definitely 31st bit is going to be 0. 31st bit is going to be 0. So what I'll try to do is I'll check, do we have its adjacent children available in this try. Okay, because at this root level, if we are trying to see for this 4, the opposite value is basically 1. That is something what we have to check. If we have opposite value, obviously we will start following that particular route, because that way only we can get the best answer at any point in time. If we have 0 available, so we have to check, do we have opposite children available at that level. Okay, because this particular try is basically built with 0 1. Okay, 0 1 again, for this particular one 0 1, again this one 0 1. This is how we are actually building this try. So at each level, let us suppose at this 0th level we don't have, at the 31st level, because this is the 31st level, and in this particular array we don't have this integer dot max value. So this 31st bit is obviously going to be 0. So at any point in time, if 0 is something about the value that we have, so we have to follow that one, because we don't have the opposite value. So obviously at this level we cannot get any opposite bit. Okay, the opposite bit is not available at this level, so obviously we have to follow that particular path at any point in time. We don't have any alternative for that one. So at any point in time, if we get the opposite, that opposite value is actually going to give us the best answer, because this is like the extreme bit that we have at this level. So obviously we have to go and follow that particular opposite bit. So at any point in time, whenever we are start traversing for this 4, the 4 is basically, first let us try to build this try. Okay, because I gave the high level approach like what we are trying to do. Let me build this try for these numbers that we have given, and based on this one I'll try to explain you like how we can figure out the opposite value for that particular 4, the best opposite that is available in this given array. Okay, for each number we will try to check what is the best opposite pair that is available, and based on that we will build the answer, and whatever the maximum answer that we are getting it, that is something we have to return into the output. Okay, I guess this high level idea is clear. If not, still let me try to build a try. I'll explain you like how things are working, then I'll explain you the code as well. Okay, okay, so just created a few of the things. See, this is our root of our try. Okay, so this the try register basically looks like this is the class that I have created. In this class we have childrens. So each children, basically this array is basically holding two childrens. Okay, this particular try, each try instance basically holding two childrens. Okay, we can even create tree. Basically we are just holding left and right children's, right? So we can even say it as a tree only, because trie is basically a tree, nothing else. So here these are like left and right. So the first children is basically holding 0, second children is basically holding 1. Okay, that is the whole idea. I guess for solving this particular question you should have this trie data structure knowledge, then only you can get these things. And obviously bitwise operations, all the bitwise operations, those also you should have clarity, then only these things will be pretty much clear to you guys. Okay, so if you don't have those idea, please make sure to learn trie. I already explained you how we can create this trie, and once you get the idea, then you can start understanding this one. And also you should have an idea about bitwise. All those things I'll explain you here, at least those bitwise operation and all. But this trie is basically a simple class which basically holding two childrens. The first child is basically for 0, second child is for 1. Okay, these two bits we are basically trying to hold, right? So now let's start building this one. So let's start to add this 4 into this trie. So how we can add it? So we have to get all the bits, 31 bits that are available in this one, in this 4. So that at 31st bit, okay, at 31st, whatever the bit that is available, it could be 0 or 1, that is something what we have to consider, and we have to add it into the trie. So at 4, 31st bit, obviously it is going to be 0. Okay, so we have to get what is the 31st bit that is available in this 4. So for that, what we can do is we can run a for loop. Okay, starting from I equals to 31, it goes all the way to I equals to 0. And second for loop is like for each number we are trying to build this trie, right? So for num from this nums array, whatever the nums that we are getting it, we have to perform logical operation. So what is that? So for this 4, okay, 4 is basically this 4 is basically represented in this way. Sorry, 100. Okay, this is how 4 basically looks, right? And we have to perform AND operation between one left shift of I. Okay, I is basically initially starting from 31, it goes way all the way to equals to 0. Okay, we are just trying to move in the backward direction. At 31st, if we want to check whether at 4 if we have any set bit or not, okay, we have to perform AND operation, and we have to shift this one all the way to 31st bit. Okay, this is like left shift operation we are performing. We are shifting one to the left side, and this basically shows that 1 0 0 0 0 all the way to 0 0. And this 4 is basically 0 0 0 0 all the way to 1 0 0. This is how this both the AND operation basically looks like. When we perform AND operation, this left shift is like we are just shifting one. We are shifting 31 times. Okay, we are shifting 31 times because I is basically 31. So this is how it basically looks like. Okay, this is how it basically looks like. And 4 is basically like this. When we perform AND operation, obviously we don't have any common bits, so this is basically 0 0 0 0 all the way to 0. That means if we have 1 here available at this point in time, the AND operation is like 1 0 0 based on the bits, the value basically generated. So at any point in time, if both the bits are set, then only AND value basically gives us the result. So if this value is greater than 0, whatever the result that we are getting it, if it is greater than 0, that means the bit is actually set at that level. Correct. So that way we can keep on checking at each level, each bit, whether the bit is set or not. Okay, so this AND operation when we perform here, this value is actually equals to 0, because here it is not 1, right? So obviously this is basically 0. All these bits are basically set to 0. When we perform this particular operation, 4 and 1 left shift of 31, obviously that value is basically 0. If the value is basically 0, we have to consider that that bit available at 31st is basically 0. Correct. That is the whole idea. So this particular bitwise operation is something what we will keep on performing to check that what is the bit available at each level. Right. So at 31st, the bit is basically 0. So 0 is something what we have created and added, because initially we don't have any children available at root level. So we have created this at root level. We don't have anything. So we have to create a new child. Okay. So children of 0, children of 0. So whatever the bit that we are getting it, if it is 1, children of 1 is something what we have to create new trie. This way we will keep on creating this trie. Okay, so initially we don't have that 0 children, so we created it 0. Now again, when this I loop started, we have to check at 30 the bit whether the bit is set or not. The same operation is something what we will keep on performing. So 0 is something what we are getting it. So this way we will keep on performing this operation until we reach to the third index. So when we shift I, left shift of 3, uh, okay, it should be 3, no, it should be 0. Okay, I have to modify these bits. Okay, because we are starting from 31st. Okay, let me correct that one also. Okay, Okay, just modified these values here. These are nothing but like to the power of 31st bit, whether it is set or not, 30th bit set or not, all the way. When we came here to the power of third bit, whether it is set or not. That is something what we are checking, and if it is not, we have to use 0 0. Now, when we reach to the power of 2, like whether I left shift of second, this basically represented as 1 0 0, correct? Whether this second bit is set or not. And obviously, this is like 0th bit, first bit, second bit. Second bit is obviously set. So when we perform AND operation between this 4 and one left shift of 2, that is 4. So obviously, this is basically going to give us uh, value. Okay, when we perform AND operation between 1 and 1, sorry, it is basically 1 0 0. When you perform AND operation between 4 and 4, obviously this is actually greater than 0. That means this particular bit, second bit is set. So here we have to create the children for 1. Okay, that is the whole idea. So when we are creating these children, all the time we are creating 0th children. Okay, in this track. But at this point in time, we have to create first children. Okay, so once we created these children, again we have to check whether the first bit is set, first bit is not set. So we have to create 0 children. Again, we have to check 0th bit is set. Again, this is like how this particular 4 is basically added here. So this is the path for 4. Okay, so this way we inserted 4 in our try. Now when we started inserting this 5, the same path is what we have to do. We have to run again first for loop starting from 31st to 0. We have to use here it is like 5 and one left shift of I, like 31st bit all the way to 0th bit. We will keep on performing this operation, and we check that based on the result that we are getting it, the value is something what we have to insert, like the children is something what we have to create. So again we check that starting from root. Again we will check whether the 31st bit is set in 5 or not. So same value is something what we have to check. Again 0 is something what the value we get it. So we check that at root level whether we have 0 children available or not. So already for 4 we have created it. So we will follow the same path. This way we are avoiding creation of duplicate values here. So same path we will keep on following because all these values are basically 0 for 5 as well. Until here the value is same. So this is the same route we will keep on following. At any point in time, if the next children that we are trying to see if it is available, our pointers simply we have to shift to that one. Once we reach at this one, again we check that for 5 the second bit is actually set, so we have to again go at this particular path. Once we reach at this one, again the first children is 0, so again we have to come right over here. Now here the first bit is set, so when we perform 5 and one left shift of 0, the answer is basically 101 and 001. When we perform AND operation, obviously this value is basically greater than 0. One is actually greater than 0, so we have to insert 1 here. Okay, so this particular path that we see, this is basically for 4, and this particular path that we see, this is for 5. So this way we are actually building our try. Okay, I guess you get this idea. So this particular path next, here, starting from here and here, this is basically representing 9, correct? Because here 2 to the power of 8, sorry, 2 to the power of 3 is basically 8. Here 0 0 and here 1. So 8 plus 0 plus 0 plus 1 is basically 9. So 9 is how, this is how we can insert 9. This particular path, okay, it is taking time to update. So yes, I'm talking about this particular path. So when we start following here, this is basically representing 6. Okay, so 4 we inserted, 5 we inserted, 6, 9, all these values we inserted in our try. Now next value is 10. Correct. So when we try to insert 10, these all the bits are 0 until here. This bit is going to be 1 because 10 is basically represented at 8, 9, 10. This is how 10 basically looks like. So here 1 is there, 0 is there. Then again we have to insert 1 and we have to insert 0. So that way 10 basically gets inserted. So let me perform that operation. At this level it should be 1. At this level it should be 0. So now 10 is also we have inserted. Next is basically last is 15. So 15 is like all these bits are 1. Okay, that way 15 is how we can insert it, because to the power of 3 plus to the power of 2 plus to the power of 1 plus 1 is going to be 15. Okay, so this is like to the power of 3, 1, 2, all these values are there. Okay, it is taking time to update. Let me take proper pause. Okay, now that we have built this try, finding the answer is really straightforward. So again, what we will do is we'll start from 4. Okay, we'll start from 4, and for each number that is available, we have to figure out what is the best opposite pair that is available in this given array. All these numbers are already available in this try, correct, in the form of bits. So we will start with 4, and for this 4, we'll start from this 31st bit. Okay, from the root only we have to start. And for 31st bit in this 4, the bit is actually 0. So for this 31st bit, the bit is 0 for 4. So we have to figure out, do we have any children available at this level? Okay, at this level, do we have any children available? The opposite children is available or not? That is the whole idea that we are trying to figure out. We just have to question here, do we have any children that is opposite for this 0? Okay, we have only two children at each level, right? So here for this one, we have two children. For this 0, we have two children. Just we have to check that at this level only, at this 31st level, do we have the second children available or not, this instance of this second children available or not. So for this 31st bit, we don't have any children available, so obviously we cannot follow that particular path. That means we don't have any number typically available in this given array that basically start with 1 at this 31st level. So if we don't have any option, we have to follow that same path. So that is how we are building the answer, because at this level we don't have any opposite children. So the answer is basically 0, 0 plus. We have to go again next. At this level also we don't have any opposite children available. So 0 plus 0 plus 0 all the way to this level, we don't have any children. But now we are following this particular path for this 4, right? So we check that at this level we are moving here for this 4. So we check that, do we have any opposite children available at this level? So obviously we have the opposite children available. That means there is another path which is having opposite bit at that particular level. At the third level, we have opposite bit. So this way we can build answer. That means like there is any number that is available, that with the help of that, when we perform XOR operation with 4, we can get best answer. And that basically start from here at this level. Correct? So it is like for this 2 to the power of 3, we get answer. So all the way from here we are getting 0 0 0, but at third level we get the answer. So 2 to the power of 3 is something what we can consider. Now going ahead, so we are now following this particular path. Okay, we are following this particular path, but we are considering the opposite bit for this 4. So now next bit for 4 is basically 1. Okay, but see, the moment we get any bit, okay, the moment we get any bit, opposite bit, we have to follow that particular path, because we have to now from here onwards we have to get opposite bits, opposite bits, okay, from this particular path. So far we reach at this level and we have to get now opposite bit in that particular path. Okay, so for 4, next bit is, it is 1. Correct? Next bit is basically 1. For this one, obviously our current children, we are pointing at this level. Okay, child is basically pointing here. Okay, that is like our current pointer is basically pointing there, because we found a path from here. We got that there is an opposite children available from there. So following this particular path only, we have to figure out whether we have any opposite child for 4. Okay, whatever the bit that is available for this 4, that is something what we can easily figure out, right? Like with the help of bitwise operators, we got to know that like next bit is available is 1 in the 4. Okay, so for this one, do we have any opposite child available following this particular path? If we don't have, we have to follow the same path, but if we have, we have to obviously consider that one. So here it is 1. For this one, do we have any childrens available as 0? Because opposite bit is something what we are figuring out. The 4 is basically represented in this way, like 0 1 0 0. Now we got to know that at this one we got 1. Correct? At this level, here at this level we got 1. So 1 is something we considered, 1 is something we have considered. Now at this one, children, do we have any opposite child for this one? Because for 4 the opposite is something we are looking at as 0. That way only the answer is going to be best. That is something what we can get it. So here for these children, do we have 0 available? Yes, obviously we have 0 available. So our current pointer, this should be current, I would say this should be current. So current should point now at this level, and 0 is something what we have to consider. 0 is something what we have to consider, because 0 children is available. If we don't have any option, we have to follow the same path. Okay, so here 0 is something we have. So our current is now pointing at this level. So current is actually pointing at this level. Now again, next whatever the next bit that is there for 4, 0 is something what we have. Okay, 0 is something what we have. So for this 0, do we have 0 available? That is something what we have to see. Sorry, it is 0, right? So 1 available, that is something what we have to see. The opposite bit is something what we are looking at from this current. Yes, obviously 1 is available, so we can consider that. So here it is 1. Okay, that is something what we have considered. Now current is basically pointing to that one. Current is basically pointing here. Okay, this is something where current is pointing. Now next bit for 4 is basically 0. So for opposite of 0, do we have any one available in this one. Okay, opposite of this 0, do we have one available in this one? We don't have one available, so we have to follow this path, and the current is basically pointing here, and 0 is something what we have to consider. Okay, so this way we can get the answer. Now when we perform or operation between these two values, obviously we are getting 1 1 1 0. So that is the answer that we are getting it. So it is like, I guess, 8 plus, no, 4 plus 1. So 13 is the answer that we are getting. Sorry, it is 14, right? So it is 2. 14 is the answer that we are getting it. Okay, this way we have to figure out like opposite match. What is the best opposite match that we are getting it? For 4, the best opposite match is going to be 10. Okay, it is going to be 10. If you try to perform XOR operation between 4 and 15, 4 is basically 1 0 0, 15 is basically 1 1 1 1. So here it is going to be 1 0 1 1. So when we get this answer, it is like 8 plus 2 plus 1, which is obviously 11. And here 14 is the best answer that we are getting it. So this way we are just trying to figure out the opposite bits. Okay, whenever we started crossing it, the current, wherever current pointing, whichever is the next bit available, opposite of that, in that current, do we have any bit or not? That is something that we have to figure out. That way only we can get the best answer. I hope you get this, like what I am trying to say here. So let me start writing the code because it is taking a lot of time to explain going ahead. So I'm not explaining you further. So let me start writing the code. While writing the code, I'll explain you the code. Okay. Okay. So the first thing is like, let's create the try. And here I'll be having 2 instances at each level, which okay. And let me define here constructor so that I can initialize these children. New try 2. We can at last, whenever we finish with adding any bit, we can add that value as well. We can set that value, but for now it is fine, because that way also, once we reach to the last bit, we can get that value, and with that value, whatever the current number that we have, we can perform XOR operation. But in the code also, there also we can do that one. Okay, logical operation. So let me keep it as it is, this try. Let me define here, or here only, let me create a root, this new try. From this root level only, we will keep on performing the operation. So first thing that we will do is, let's start this getting this nums. Okay, for each num, we have to insert it into the try, right? So we can get nums. Okay, so let me define here, current is basically equals to this root. From this root only, we have to fill these numbers, whatever the numbers that we are getting it, into the try. So next for loop is like, for I equals to 31, I should be greater than equals to 0, and I minus minus. Okay, we are basically checking all the, from this 31st bit to 0th bit, whatever the bits that are available in this current number, this number, those values are something what we have to add it into the try. Because since these nums are basically, it is clearly mentioning in this one, they are basically integer dot max value. Okay, that is this number's value all the way going. Okay, once we are done, what we have to do is we have to get the bit. Okay, so currently let me create here a bit is basically equals to 0. We check that if this current if this num and one left shift of I, okay, that many times we are performing this operation, if this value is basically greater than 0. Okay, if this particular value, if it is actually greater than 0, that means we can say that that particular bit is basically 1. Okay, in that particular num, correct? So once we get the bit, what we have to do is we have to check that in this current, do we already have that children? Okay, so if current dot children, uh, this bit, if we already have, if it is not equals to, if it is actually equals to null, we have to create it. If we already have, we can simply point to that one. So what we can do is we can create current dot children, this particular bit equals to new try. I'm creating this new instance of this try. Okay, so 0th, at 0th one, we have created 0 and 1. Those are the 2 instances that we have, right, at each level. Yes, I have created it. Now current should start pointing to current equals to current dot children, okay, of that particular bit, so that we will keep on shifting our pointers downside. This way we can build our try. Okay, pretty much clear, straightforward. Obviously, like you should have all these operation ideas and all, then only you get these things. Okay, so first make sure to practice those things, then only start solving this type of questions. Okay, Once we build our try, this is how we can build our try, and that try is basically built. We have to get the maximum between these two numbers. Okay, so max answer is something I'll define here. It should be 0 for now. Let's again start going through these nums, int num from these nums. Next one is like obviously once we are getting these nums, right, we have to get the bits also. So again here let me create the tag from this try only. It should be current, should start pointing to this current. Again the same things I'm doing it here. So int I equals to 31, I should be greater than equals to 0, I minus minus. So at this point in time, let's define here current max answer as well, which is basically 0. Here itself I'm building the answer. Okay, so at this 31st, again I have to get the bit. Okay, for this any number that we are going on. So for this three, whatever the 31st bit is there and all those bits are something what I have to figure out. So again same kind of operation I'll perform here. So if num, this whatever the num that we have, num and one left shift of this I, if it is actually greater than 0, so bit is basically equals to 1. So if bit is actually 1, okay, if bit is 1, so we have to get opposite of that. If bit is 0, so obviously if this value is not greater than 0, the bit is basically equals to 0. So opposite bit is available or not, that is something what we have to see in this current. Okay, so whatever this try that we have in at that level, at each level, do we have any opposite bit available? So how we can check it? Like if this current dot children of this bit XOR one, like just flipping that bit. If we want to flip that bit, like if we want to get the opposite, obviously we have to use XOR operation, right? I already explained like how bits are basically getting checked in this XOR operation. Okay, XOR operation. We check that if it is actually equals to null. Okay, if it is actually equals to null, then we have to generally follow that path. If it is not equals to null, if it is not equals to null, so whatever the answer that we are getting it at that level, that is something what I'll add it into this current max answer. Current max answer or operation, that is something what I can perform here. And one left shift of I. So here that particular bit, one left shift of I means like if 31st bit is set, so to the power of 31 value, whatever that we get it, I am performing our operation with this current answer. So that way we can keep on building the answer. So whatever the bits that we are getting it, the opposite bits, those will keep on performing our operation with this current max answers, so that we can get the answer. This way also we can generate answer. Once I perform this particular one, the current should point to current equals to current dot children of this bit or 1. Okay, or else if not, it is not necessary to perform this particular operation, because I mean 0 is something what we have to consider, right? So doesn't matter, we don't need to update this one. So current equals to current dot children of that particular bit. So we have to just shift our current pointer to the next bit. This way we will keep on trying to get opposite bits, and we can get the best answer in this current max. The moment we get the best answer in this current max, this whatever the max answer we have outside, max answer is equals to mat dot max between max answer and this current max answer. Out of that we have to get it. Once this particular is done, we have to return this max answer. For each bit we are trying to perform the same operation here. Let me try to see if it is working fine or not. Okay, there is compiler error, line number 26. Okay, num and one left shift of I. So yes, we have to add here brackets. Okay, yes, that is the only error. Let's see if it is working fine or not. It is getting accepted. Let me submit this code as well. So talking about the complexity now, here the first for loop is basically running n times. Okay, if we have n numbers, second for loop is running 31st times, so it is like n cross 31. Those many times only we are running it. Similarly here also we are running first for loop as n times, and second for loop is running constant, that is like 31 times it is running. So obviously complexity is going to be n cross 31. And space is something like we are just building this try. That is also like building this try is obviously going to be if we have n numbers, so n nodes have each 32 bits different, so it is going to be n cross 32. That is going to be n only, obviously. Okay, So both the time it is going to be n cross 31 or 32, we can say that, like, okay, because it is going to be starting from 0 all the way to 31. That means like 32 bits we have, right? So obviously we can say that. So n cross 32, n cross 32, both the time and space complexity is something what we can get. I hope you get this idea. If not, please tell me like where you are struggling to understand this one. But yes, obviously we have to understand these things first, okay? Then only you get these things. So make sure to first understand, try, make sure to first solve bitwise questions. Then only try to solve this one. Then only you get these things, okay? So yes, thank you for watching this video. Bye bye.